Today I will introduce a trigonometric form and exponential form to you. And at first, I will give you some basic introduction of complex number. Take for example, 3 equals to 2 plus 4i. And we can show this letter as a graph, and the modulus of a complex number is the length of this vector. And the argument of a complex number is this theta. And here's something you need to pay attention is the argument of a complex number's range. The range of the argument of a complex number is 2 pi. And when we discuss about the principal arguments, and this is minus pi to pi. And we denoted this by capital A, G, C. And here's our main part. I will first introduce trigonometric form to you. And this is its definition. The polar form or trigonometric form of a complex number c equals to a plus bi is c equals to r multiplied cosine theta plus I sine theta, where a equals to r cosine theta equals to r sine theta, and r is this value. And I will give you some example later because there's a comparison between trigonometric form and exponential form. And now we will use this form to talk about Euler's formula. To prove this interesting formula, we need some extra knowledge. We need Taylor series, and I give you in this. To get this formula, we could plug in x equals to I theta to this, and we will get ei theta equals to theta and if you compare this part and this part, you will find this part is very similar to this. Actually, it's the same. This part is the same to sine x, so we'll find and then we'll talk about an interesting connection using Euler's formula. That is, if we let theta equals to pi, and to plug in the formula, we will get e to I theta I pi equals to cosine pi plus sine pi, and cosine pi is -1, while sine pi is 0, so we will get this interesting formula. And now we will talk about the exponential form. And here is definition. a complex number z with a modulus r equals to z and argument theta can equals to r argument z can be written as this form. And here's some interesting properties about exponential form. That is, the exponential form follows the same rules as real exponentials. Take, for example, to prove this form, we could use Euler's formula, and I will write it here. And e to I multiplies theta 1 plus theta 2 is cosine theta 1 plus theta 2 plus I multiplies sine theta 1 plus theta 2. And use the formula of trigonometry, we will get. And if we discuss about this, using the Euler's formula, and we will get cosine theta 1 plus I sine theta 2 equal cosine theta 2 plus I sine theta 2. There's a mistake here. And we will get this. And if you compare this with this, you will find these two is equal. And this is the first property, and there's no more space, so I will clear it and show the next one. E to I theta bar. And this time we need to use some extra knowledge. We need to use this one. And it equals e to I theta bar equals 2I plus I theta plus I theta square over 2 factorial plus this. And because this is a bar, and which equals to this. And now is the comparison part. We will compare trigonometric form and exponential form here and give some example to you, which will let you have a deeper understanding about these two different forms. And first, we need to turn Z1, Z2 into trigonometric form. Z1 goes to 3 minus 3i. According to the trigonometric form here, we need to get R, which is the modulus of the complex number. So R equals to this, and we need to get R cosine theta and R sine theta, and this time we could use the graph. The argument of Z1 is minus 4 pi. So Z1's trigonometric form is, and now let's discuss about Z2 using the same method, using graph to get the Z2's argument is equal to swing pi over 3, and its modulus R equals to is 4. So Z2's that's okay. So Z2's trigonometric form is 4 multiple cosine pi over 3 minus sine pi over 3. Yes, there has to be an I here. And now we could start to calculate its exponential form. And let's see its definition. Exponential form, yes, modulus R and argument theta. And Z1's exponential form is equals to, this argument is minus pi over 4, and Z2 is e to 4 multiply e to I multiply pi over 3. And now we can start to calculate Z1 multiple Z2 and Z1 over Z2. And first, we start to calculate this, Z1 multiple Z2. And we will go this. And if you use exponential form to calculate this, we will get the answer in an easy way because we have proved the exponential form has the same rule as real exponential forms, real exponentials. So the answer is and we can turn this form using Euler's formula and get the final answer. It looks complicated now, right now, but this is because the angle I give is not easy to calculate. But in most situations, for the multiple and for the division, exponential form is more easy to calculate than trigonometry form. This will be more obvious if which I show division part to you. This is the trigonometric form, and if we use exponential form, it will in easy way. Yes. This looks more simple, obviously. And now we can go to the next part, some interesting properties of exponential form. And first one is the argument of Z1 multiple Z2 is equals to argument Z1 plus argument Z2. We could use exponential form to solve this problem. Z1 multiple Z2 is equals to R1 EI E2 I theta 1 multiple R2 E2 I theta 2, which is R1 R2 EI theta 1 plus theta 2. And its argument is obviously this theta 1 plus theta 2. And the argument of Z1 EI E2 I theta 1's argument is theta 1. And this is theta 2. So it's equal. Let's discuss about this. is the same. Z1 over Z2 is and its argument is theta1 minus theta2 and is the same as argument of Z1 minus argument of Z2. This is the end of the video, and I hope you like this video and can learn something from this video.